That's fine. Some people see this as a way to double check afterwards. And so everybody's tossing different ideas. And so what I'm going to go, yeah, I mean, they're all loaded up. You can watch them anytime, but I'm basically going to just make one final decision and stop like input. So option one or option two, your opinions. Make the schedule so that the lectures I do happen just before Coy does them the next week, um, or stick all physics for a while, O come for a while, G come for a while. So who is for the try to base it on the actual schedule? So 1, 2, 3, 4, 5. Okay. And then how many just do a block of physics followed by a block of GChem, block of OChem? Like I set it up this time. Okay. Okay, so it looks like about a 5-to-1. Yeah. And I mean, eventually all of them will get there. It's like it's not no matter what we cover, it's more when we cover it is become the input. So I'll go ahead and I will send out a revised schedule then based on that. So next week I will add thermo. I will move sound and light and optics to later on in the session. And so look for an updated thing. I'll send it to Jonathan. And sorry to do the switcheroo, but once it's set this time, we are set and it is on, and this is what we're doing. Maybe force and energy at the very end thing. And again, this is a case where I'm getting too many people asking for too many things to navigate it as well as I once could. So let me send out that schedule. It did not have forces, but it has 2 open days. So adding them on the left at the end. Thermal will end up being this upcoming Tuesday because it was covered recently, so I want to get into it early. And then everything else will move to a few days before it's actually given. So hopefully that seems okay. So again, I'll look for that schedule. I have 2 holes in it still to fill various things. I'm not going to promise anything until there's enough feedback from everybody, because that's been the issue is I've been making adaptations based on one person's request and another person. So decided this plan has not worked out quite as well. So, ah, oh yeah. So, Elton, are you not in this current group's Discord page? They ditched the old Discord, that outdated old one from your class, and have a new one. So, anyway, all right, good timing. Let one more person in, and we will be good to go. Thank you for letting them in. You're in the new one or the old one? Okay, perfect. Okay, then you're good to go. Okay, so starting into this, so electric circuits, um, for what it's worth, the MCAT, they simply say circuit elements. And so I'm going to take that to heart because a lot of what they do is exactly that, just what happens to a certain circuit element within a circuit. So this is that rare lecture where there's not a large amount of information. There's just so many different ways to apply it and look at it. And so what I want to do is I want to go back to the point where you first started learning circuits. How many were freaked out the first circuit you saw? I cannot reload the new schedule because I haven't finalized it until I saw your input. So sorry about that. I mean, I'll let you guys can figure out how to send it. Oh, was that message meant for me, or were you private messaging somebody else and accidentally because I was the last person sent to? Yeah. Okay. So ask about the circuits. Okay. Oh, I'm getting different things. Okay, yeah. So for most of you, first time I saw it, like a few of you mentioned, it was intimidating and weird. Did anybody find it got easier in time? Yeah, there's 2 people sitting to be let in, and my cursor is just not conveniently going to the spot. Okay. Oh, no, 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 no. Oh, shoot. Okay. I got to exit out because of just a second. Sorry. Oh, I have no idea what to do. My things froze up because I just hit remove for somebody and my cursor is all screwed up. Okay. Yeah, I can't, just word to the wise. I cannot at this point let anybody into lectures after a minute or two afterwards because of just what happened is when I try to do it, if I hit the wrong button, it freezes everything up. So just, I mean, just gonna have to come up with a better system. So sorry. I don't think, nope, you're here. So I apologize if you were stuck there for a while because I accidentally hit kick you out instead of let you in. And so you were hung in the middle. So sorry about that. Okay, circuits. Back to the focus of this. Circuits, when I learned them in school, honestly, overwhelming when I first saw them. It like opening up a booklet how to put your stereo together and saw that circuit like, oh, and closed it and ran away. But I noticed over time, circuits were a lot like Sudokus in that they're weird at first, but once you get your rhythm, once you figure out how to solve them, they get easier and easier. So did anybody pick that up in time and realize circuits were like a puzzle more than a question? They were actually kind of fun to figure out if you knew what this element did, you could figure out what another circuit element did. Did anybody reach that point? Okay, 1, 2. So I'll go with the survey of 2 says they're fun. There's something fun about them, and that's hopefully going to be my goal. Get them to a point where you kind of enjoy and see the ease of them. The MCAT, generally speaking, will try to make them reasonable questions, but there'll be a couple weird ones. Like if you've done the section bank questions, there's one on there that's just the circuit question from hell. We'll look into something like that, but by and large, they still follow basic rules. So starting with this, everything on the MCAT is an RC circuit, so we're only going to worry about resistors and capacitors. Okay, so a resistor opposes the flow of charge. It offers a resistance, i.e. friction. When you have friction, you can generate things like heat. You can generate magnetic fields when a charge moves, so you can also do work with magnetic fields. The energy drained by a resistor can be given off in many different forms, light, heat, work. A capacitor, like the word implies, capacit, like capacity, has the ability to store charge. Capacitors naturally would want to be neutral if they had their choice. They don't want to have a charge, but can you force charge to build up on something? Just like, can you force a ball to go uphill? It would rather be downhill, but you can push it uphill. You can move things to less stable positions. You can move current to charge up a plate and store it for whatever reason we're going to use it for. But basically, capacitors, you force charge to build up on plates, you store charge, and resistors, they inhibit the flow of charge, and in doing so, drain energy. Before I get into that, the basic concepts, conduction. So conduction is defined as the migration of charge from one point through a defined space. For our purposes, it's going to be down a wire. Oh, yep, let me exit out. Totally forgot of everything I forgot to do. I forgot to load that. So I will send it. I please ask, nobody send me a personal message for the next 8 seconds or so, because I've done that. Okay, so it should be up now. You can send all the messages you want. Sorry, completely spaced on that one, but at least everybody got it on the right side. So sorry about that. Okay, so I'll give you a second to download that. Okay, so conduction is the flow of charge down a pathway. For our purposes, it's going to be down a wire, but can it also be charge flow through a neuron, for instance? Is that also a way they can ask? Sure, it can be any type of charge going down any type of pathway, which means we're going to worry about the rate, known as the current, how fast the charge is moving, and then we're going to worry about the path it chooses. So generally, they choose path of least resistance. In general, what's a better pathway, a wide pathway or a narrow pathway? For water, charge, cars, objects. The wider the pathway, the easier it is for stuff to flow. More can flow. So generally, as a pathway gets wider, it's less resistive. So let's look at neuro. Which has more resistance, the central nervous system or the peripheral nervous system? Weird sort of question, but hopefully you can answer it based on that simple narrow-wide question. Why does the peripheral have more It branches out, exactly. Starting from the brainstem, the ganglion, as it branches out, do you agree? It goes from a thick pathway coming out of the brainstem, and then gradually as it fractions out, by the time it gets to extremities, do you agree? It gets thinner and thinner. Branching gets thinner, so resistance is higher. Charge is harder to flow through periphery than it is central, which makes sense. Which one is processing far more information per second? A path in the central nervous system or a path at the extreme end of your peripheral? Yep, central. So central has to be wider, more current has to pass through it, more charge has to pass through it, if that makes sense. So the same rules that apply to circuitry apply to the nervous system. And how many learn that? How many learn, for instance, wires are insulated for better conductivity? Neurons are also insulated with myelin sheath for better conductivity. How many learn that if two wires are not insulated and they touch each other, you can short circuit? How many learn that MS, when you end up losing your myelin sheath, if two wires hit, they can have seizures, spasms. They can have, mistransfer of information. All the above. There's definite correlations. So learning one will help you with the other, physioics. Okay, so with that in mind, conduction, let's consider this wire. Do electrons travel just on the surface? Can they travel in the core? In theory, can they travel anywhere on that wire? Yeah, they travel easier on the surface because there's less things holding onto them. But migration from one end of the wire to the other could be in the core or the surface. We're going to not worry about where the electrons are traveling. We're going to simply worry about the fact that they are traveling. Okay, so with that in mind, is it a case of one electron racing across the surface like that? Or is current more the flow of multiple charges? So is it a case of one charge, or is it one hits another hits another? Multiple charges, exactly. It's like a line at a theme park. One person steps up, everybody moves in the spot. One person steps up, everybody moves in. So it's flow of a migrated pathway. Okay, reality is electrons are light. They're easier to gain and lose because they're light. So all charge is the result of electrons moving. However, you have the old LA stop and go. So except picture everybody actually being smart enough that when one person goes and nobody's on their cell phone, they all move. So yeah, it's not the perfect visualization, but when one goes, they all fill its place. So it's fast responding. So it's almost like, you ever seen a stream of fish swim or birds flow? They all move in that unison. That's like a flock of birds all taking off and going in the stream like that would be a good example. Okay, so next question. Do physicists believe in reality? Dang it, what does that mean? They actually don't believe in reality. Because although electrons are the thing that flows, and every scientist in biology and chemistry knows this, what do physicists say it? How do physicists say the flow is? Or what do they say the flow is? Imaginary positive charge. So they assume it's a positive flow. And in the end, it doesn't matter because a negative moving to the right would leave an absence of an electron over here, so a positive, and a negative buildup here. A positive moving to the left would have an accrued positive and an absence of positive or negative on this side. Do we get the same result? If you picture electrons going one way, is that the same result as positive going the opposite way in the end? Sure. So we know our car drives down the road. We know the road stays stationary and the car drives. But to the physicist, the car is stationary and the road is moving underneath. Do we still end up down the road either way? Yep. So never trust a physicist to drive or teach you anything, but fair enough. So flow of positive, I'm going to stick with electrons for this slide. I'm going to jump to their make-believe world next. This is known as electrical because it's electrons. Conductivity, we see this in metals because metals have low ionization energies, low work functions. They hold on to electrons loosely. So they can leave, go to the next spot, next spot, next spot. They can jump from atom to atom or place to place. There's also a second type of conductivity known as electrolytic conductivity. And so picture the following, if I can get my screen to work. There we go. So if I have a bunch of plus charges inside some confined space and some in between inside, so let's just call this, I don't know, let's say it looks like a battery, a galvanic cell. Let's just call it a cell. Let's say this is intracellular and between cells, intracellular between cells. No, totally hypothetical. But if I could somehow inspire this, polarize, make a dipole, somehow move charges over to have charge on one side, can I move all the charges over? And if they do, will they end up repelling these, which in turn move this way, which in turn repel those? So can you get this sort of cascade effect? They all move. So even though these charges never left their home, these never left the space, they never home, left their space. Yeah, I guess in a certain way, it's like a van der Waals force where they all push down. So van der Waals typically are induced dipoles. These are more just an actual cascade. But if they all move over, it's not one type of conductivity. And then they relax, and then you do this again, then they relax, do this again. Can you send a signal in that way? Can you send this pulse of charge down a pathway? So does anything actually transfer charge that way? Is there any sort of conductivity that does that, even though I hit way too fast? Yep. Is that in essence the way nerve conductivity works? Depolarization of one cell next to one, next to one, next to one. And are there any points of node displacement or node something? So where do you get node stuff happening? Are there nodes? Are there empty spots where things don't jump? And I don't know, in physio, is there anything in the nerve that has the word node in it? Node Renvier, exactly. So is that the space that the charge will move up to, then cause repulsion in the next one, repulsion in the next one? So whereas charge migrates all the way across, you actually never have charge leaving that wall right there. You never have wall leaving that wall. So it's not the perfect example, but is there a word node right in the physiology of nerves? Yeah, if you will, that's where the repulsion, get right up to there, it repels the ones on the other side to move over, which repels the ones on the other side to move over. So is that what they call it in physio, a leap? Yeah. So it's technically just the charges all push up against it and they cause everybody in the next room to move over, next room to move over. So you actually get no actual charge migration across that point. Okay, so hence the word node, just where it pops up. Okay, moving onward, I'm gonna go into just basically a physics lecture. Physio is gonna pop in from time to time like that. But a resistor, again, offers resistance. How many have seen this notation, the squiggly lines? Hopefully it's standard notation for a resistor, okay? They drain energy as current flows through it. It ends up, again, friction. So I'm going to tell you a device and you tell me if you would say it's a resistor or not. Okay, so let's say I have a space heater. Let's say it drops, like right now, it's getting cold where I'm at. It's all the way down to 81 today. So if it drops below 80 and I might need a space heater, could I send current through my space heater? Sure. And when it causes that friction, the wire heats up, blow air across it, ta-da, you got it. Or a hair dryer. In fact, are those usually your biggest offenders? Space heaters, blow dryers, microwaves, things that have a lot of power in a short span of time. Okay, that's one type of resistor. Is your television, your computer, is it also a resistor? Is current going through it and is any energy coming out of it? Is it warm and you see bright light? It's a resistor as well, giving off, in that case, light and heat. And then even a motor, an electric motor, you send current through it, creates a magnetic field. That magnetic field can cause another magnet to turn. And in doing so, you have this whole, I guess, motorized process. A spinning crank can eventually be turned or connected to a wheel and create some electric vehicle. Okay, with that in mind, I want to go through the very basics of this, and that is resistance, how much the wire resists, depends on a few things. Do you think it should depend on what the wire is made of? Are some materials going to allow for electrons to transfer more than others? Sure. What do your instincts tell you about metal compared to non-metal? So metals with a lower ionization energy typically allow or don't allow. Metals allow. Easier to have an electron leave and move across. So metals typically have lower resistivities than nonmetals. So if you want to insulate, you have a very high resistivity. That means high resistance, current doesn't flow. You have an insulator, a nonmetal, plastic, rubber. So again, myelin sheath. Myelin sheath is made of copper, I think, or maybe it's made of steel. I can't remember. What is a myelin sheath made of? Ah, fat. You're talking about the thing. You're not calling me names, I hope, but fair enough. So yeah, it's at any rate, no, it's this chunk of fat, lipid on the outside. Perfect. Why lipid? And by the way, I'm totally joking. I'm so sorry if that ruined the tone of the lecture. You mind? I was just totally joking. So sorry. Carbon-based, exactly. It's a non-metal, doesn't transfer through, but the core should be conductive. So that one's an aqueous-based thing for electrolytic conductivity. In our case, we want a metal wire and a non-metal insulator. Perfect. So rho has to do with the material. I think rho stands for density, doesn't it? So a couple things. Physicists not only spell horribly, but do they also use the same variable multiple times when Lord knows there's so many other ones they could put in? Yep. So although it's density in other scenarios, this one is resistivity. Lord knows they couldn't use like delta for density, start with the same letter, but yep. So this is not density, this is resistivity, same letter, same everything. So like somebody just said, you got to recognize it in context. You told me earlier, wider pathways offer less resistance. Yep, exactly, that whole context. So in fact, going off on a site term, isn't that called the Gestalt principle? That you can't determine what that is until you see it in context and what's surrounded. I mean, I still love that example of the 13er B. Same thing here. This row, only in context when I see it here, as opposed to in a density context. Wider resistors, less resistance. Why would longer resistors have more resistance? More friction, more stuff to go through. Longer to take the pathway, more stuff you're going to run into. Perfect. So let me see if that makes sense. Let's say I take two resistors, R1, and connect it to R2. Resistance goes up or down when I add those two together. Let me make it R equivalent. Why does it go up? Longer. You have two pathways to go through, one resistive, another one. And how many learned that R equivalent in that case is R1 plus R2? How many learned that longer equals more resistance? Okay, fair enough. So help me out with wider. I'll do wider in a different color. Let me do wider in green. You're at the grocery store. Mind your own business, waiting in a long checkout line. When all of a sudden another check stand opens, no matter how slow that new checker may be, is it still better for everybody to get out of the store? So the question is, does that other checker open up in parallel or series? So do you now have to go through two check stands, or do you now have a choice of one or the other? They are said to open up in parallel. Because they open up in parallel, they made a wider pathway. So in this case, it's wider. So R equivalent, when I asked, does it go up or down? Because wider actually goes down. Somebody learned that R equivalent for parallel pathways, 1 over R equivalent equals 1 over R1 plus 1 over R2, etc. Now, if I think about it, anytime I add two numbers together, two positive numbers, when you add them together, do you always get a bigger number? I mean, how many learned that? Any two numbers, when added together, you get a bigger number. So if this is bigger, if this number is bigger, one is the same. Does that mean the denominator must be larger or smaller in order for this sum to be bigger? if I add two numbers together, collectively they're bigger. That means if this number overall is to be bigger, it's because the denominator must be smaller. And when in doubt, plug in numbers. Which is bigger, 1/7 or 1/3, for instance? 1/3 is bigger? Exactly. So if collectively adding these two together, 1 over R1 plus 1 over R2 together, anytime I add two positive numbers together, the total sum is a larger number. So 1 over R equivalent has to be larger than each of these two individually because I've added them together. So if it's larger than these, that must mean this denominator must be smaller than these. Does that make sense? And yeah, I probably didn't explain it well, but hopefully it makes a little more sense in that case. When I add two fractions or two numbers together, if they're both positive, then this number has to be bigger, so it has to be a smaller denominator here than I had here and here, meaning R equivalent is lower than the individuals. So add things in parallel, easier to get through. That's why area is in the bottom. Area goes up, resistance goes down. Add them in series, it goes up. So is this equation kind of the root of what we already know or what we learned in physics about adding resistors together in series versus parallel? Yeah, yet it's so simple when you look at it that way. Yeah, and it makes more sense when you make things wider. Okay, so I think I'm getting this. So I'm going to move onward and upward. Everything I have on there, I'm going to have to erase because the sentence is going to come in right there. So erasing in 3, 2, 1. Sorry, it's all gone now. Long resistors have greater resistance. Wider have a lower resistance. Longer is similar to series. Wider is similar to parallel. Okay, perfect. Feel pretty good about this. So onward we march. Energy can be drained, as mentioned earlier, heat, light, or torque, where torque can be used to turn a wheel, which ultimately does work. So lots of different resistors on this planet. They just drain energy. Okay. So just to summarize what we did current-wise, if I have two resistors in series, just like you mentioned earlier, we add R1 and R2 directly. Altogether, R equivalent, because it's a sum, is greater than the individual one. So adding them in series makes a longer resistor more resistive. So if this was 2 and this was 3, this is 5. 5 is bigger than 2, 5 is bigger than 3. But in parallel, it's an alternate pathway, so we have this. How many of you are signing up for the version of MCAT where you get partial credit for showing your work? Oh, you mean no, they don't have such a thing? Dang it. So is showing my work doing me any good other than wasting my precious time? Then screw it. I don't want to show my work, so I'm going to do this. I'm going to rewrite my equations to make life a little easier. I'm going to make that R2 and R2, R1 and R1. So now I have a common denominator of R1 times R2, R1 times R2. And so I'm now going to have, I'm going to write it as equal over here. 1 over R equivalent. It looks like a smiley face. I don't like smiley faces. Sorry about that. A scowl much better represents this. R2 over R1, R2. Plus R1 for R1, R2. Which then equals R1 plus R2, the sum over the product. But wait, do I want 1 over R equivalent or do I want R equivalent? R equivalent. So can I just flip this fraction around and end up with this relationship right here, product over sum for two resistors? Life gets so much easier. So for instance, if this equaled 3 and this equaled 7, you could calculate it as 1 over R equivalent equals 1/3 plus 1/7 and just have a good old time doing math. Or could you do this in your head? What does 3 times 7? 21. What is 3 plus 7? 10. What's 21 over 10? Perfect. Is 2.1 less than 3? Is 2.1 less than 7? Yep. So it meets that restriction, which we already knew. And mathematically, do you believe me that 1/3 plus 1/7, if you go through all the work, you eventually get the same thing? Oh, you're very welcome. It is so much easier to do this way. So I will rederive if you so desire. Let me get rid of the red. In fact, I will derive everything from scratch. Although you do know I hate the D word, right? So I will mathematically manipulate. So what I did is I multiplied this by R2, top and bottom, this by R1. My goal was to get a common denominator of R1 times R2. So this term becomes R2 over R1 R2 plus R1 over R1 R2. Because R1's numerator, that's my common denominator. I'm now going to rewrite that as R1 plus R2, just because I like sequential order. So I add in numerators, R1, R2, over the common denominator. That's 1 over R equivalent. And then I just flipped it around. Move that on top, move that on top, and I got this. You never get to ask again, because how important are derivations? Not at all. End result, very, very important. So doing it one time is fair game to believe it, but do you believe it? That said, it does not work for 3. You have to do it differently. So if I wanted to get it for 3 resistors, R equivalent for 3 in parallel would be R12 times R3 for R12 plus R3. In other words, I'd have to solve it once for 1 and 2, take that number and plug it in here, times 3 in that, which means this is awesome for 2, still kind of useful for 3, completely worthless for 4 or more. So it's a trick for 2 and possibly 3, nothing more. Fortunately, what are most circuits they give you on MCAT? 2 with an occasional 3. So it's a great trick. It's a really cool trick. And guess what? It also works for capacitors. So for parallel, product over sum. Hang on to this, because this derivation I just said, don't worry about it ever again. I'm going to end up using this again for capacitors. I'm going to use this when I do lenses and mirrors. I'm going to use that same concept for a few other things. And you're going to hear me say the same thing. Don't ever derive anything, as I keep deriving other things. But it ends up being a really cool little trick. Repeat, I get no partial credit on the MCAT. So why show my work when I can do this sort of thing? It is so much easier to do it this way. And we're going to apply that as much as we can today. Okay, last note. Notice the capital letters that sort of snuck in there in bold red capital. In series, you're stuck. If you're going through this pathway, you're going through this pathway. Everybody marches at the same path. When you go through parallel, you get a choice. You get a path of least resistance. So in parallel, you get different flow rates, different currents, but the same in series. However, in parallel, you get the same voltage drop. Otherwise, it would flow backwards. So whatever voltage comes in here, I get the same drop through this as this, because if it was different, then current could flow backwards, which it does not do. Have you ever seen water flowing, traffic flowing, current flowing? It goes, it may split up, but it comes back together and keeps going. So the voltage drop is the same in parallel. So I want you to remember this phrase. We're going to use this a lot today. Is VP. It is very important. Is VP current, series, voltage, parallel. So same as VP. Same current in series, same voltage in parallel. Is VP? Hang on to that thought, because we'll use this. Okay, onward and march. So R equivalent, when you set it up in series, R equivalent goes up. When you set it up in parallel, R equivalent goes down. Parallel makes it easier, series makes it harder. So are our circuits in our house wired in series or parallel? Our outlets are wired in, huh. Well, let's make a decision. So a couple answers popped up. So let's go by my personal experience. If they're wired in parallel, does that mean they get their own individual voltage? So if I plug another one in, this one is unaffected, just another one. But if they're in series, if I plug another one in, will it suddenly take some of the voltage and therefore have less voltage for the next one? So what happens when you plug in? Your TV's going, you plug in your computer to recharge it. Does your TV dim and get less bright and slow down, doesn't work as well? Or does everything work about the same? Yeah, your house explodes? Nope, works the same, which means everything in your outlets is wired in series or parallel. Your outlets are in parallel, but it's a trick question because is everything in series with your junction box? So there clearly are certain things in series. So your circuit breaker is in series. Exactly. If your circuit breaker trips, everything along that line trips. So your outlets are in parallel, but it feeds back to something in series. Is this exactly like what happens with your neuro? Everything's in series with the brain, but then does it split into parallel when you get in a peripheral nervous system? Okay, so this test you did, the holiday light test you just talked about, is that one where if one light goes out and they all go out, they must be in series or parallel? Let me give you a different one. Let me give you a slightly more practical one. Hypothetically, let's say this is purely hypothetical, nothing real about this. Let's say your wife got a car that had a headlight like this and had these cute little dot lights that would, for every dumbass reason, were really popular about 5, 6, 7 years ago. And let's say you borrowed her car, hypothetically speaking, and maybe lightly tapped into something with the front corner of the car ever so gently. And let's say you might have accidentally knocked out that light. Hypothetically, this is all hypothetical. And what you discovered was the headlights still worked just fine, but that these also went out, all the cutesy little circle lights. This is totally hypothetical, and I don't appreciate the accusations. Hypothetically, would you say these lights were wired in series or parallel? These are all in series, but the headlight, the really important one, you agree would be silly to have it in series because if one light goes out, you don't want all of them to go out. So is the headlamp, the actual important one, in parallel? The cutesy lights are just series? Thank goodness, probably a learned behavior. So if you're driving down the road in Southern California at night, and maybe you see a car that has one headlight and the other headlight with some lights next to it, hypothetically, that might be my wife's car. We don't know. You just don't do it because maybe when you went to the dealer and they said to replace all of these was like $1,900 or something insanely crazy, really smart design, you said, I think it looks kind of good without them. Hypothetically. Yeah. So at any rate, yeah, that's a case of series and parallel for hopefully good reasons. Applied to physiology. Are there certain spots, God forbid, if you pinch a nerve or sever a nerve, that it causes paralysis? Which means series or parallel? Perfect, series. Okay. Now, is there a certain point in your spine where you get below a certain, I think the third and fourth vertebrae, or I don't, I need to answer this one carefully because I don't know my physio well enough. But is there a point where you go having less paralysis? So why is that? Why is there some point where suddenly, if you sever below a point, maybe it's only the lower extremities? You start the branching process. So somewhere down your spinal column, do things start to branch off? Parallel pathways, unaffected. So if you pinch a nerve in your elbow, you agree your shoulder is going to be fine. If you pinch a nerve in your shoulder, is there a chance your elbow will also be messed up? Does that make sense or seem reasonable? Okay, so you get it intuitively, makes sense. Just note then parallel, break the pathway, the rest is good. Break it in series, you're screwed. Yeah, so why would you ever wire anything in series? Convenience, literally less wiring. You want to carry all your charge from the power plant to wherever in series, so you don't have to have all these different pathways and therefore a little more wasteful. But once you have specialized need, then you branch out. So hopefully that makes some semblance of sense. So your brain, you want to have all the central processing there. It must be in series with everything. But eventually you want to get to parallel so that your motor functions are not dependent on other parts of your body. You really don't want your left hand to need your right foot to move in order to work, so to speak. But you want your brain in on all of it. Hopefully it seems okay. So onward we move. You have 10 seconds to get this right, even though it'll take 30 seconds to read it all. All right, first two answers are in. A few more answers in. Okay, looks pretty consistent. How many found the hardest part of this question was staying conscious while reading through and not losing focus and getting bored? Occasionally it's like that. So tell me about muscles. Series or parallel? Parallel with the goal of individual stimulus, which means D is in, damn, did he have to make it the last choice so I had to read everything? Yes, that is why I picked D. Mean, evil, subtle things you can do as a teacher. But how many find this question unbelievably easy, but really, really pain in the butt to read through everything? Makes sense, it's intuitive, but just damn. That said, the one that I'm inspired by, what they may have done was far easier, less reading, but they weren't, A and B weren't so similar, C and D weren't so similar, but the same basic concept. Okay, I feel good about this. Onward we go to capacitors. Again, capacitor has capacit right in it. It's like capacity. You store charge on it by forcing it to go on. So typically, the example we use are two parallel plates. So what is this? The unequal lines. I know I'm supposed to recognize that, and I don't, but luckily you're here to help me. It's a voltage source. It's a battery. It's an EMF. It's something that moves it. I forget. Am I supposed to know what the little one and big one are from a few of their lectures? Little Orphan Annie, Fat Cat, perfect. So if you like that movie, it works out. Oh, that was not supposed to happen. This was supposed to happen. Make it more A-like. So because I'm doing physics and not GChem, I now need to actually get into crazy mode, and that is currenta. Instead of current, we're going to call it currenta. Currenta goes from C to A. So in my currenta model, current goes from cathode to anode, meaning current's going to go from here to here. So this one is being forced to be an anode. Current's going to go from here to here, forcing this one to be the cathode. Okay. Perfect. So we're all over this. So cathode, current's going to flow. What I want you to tell me, is it going to be faster for current to go from this cathode to this anode, or this cathode to this anode, being that it's the exact same distance? Which side is faster, left side or right side? Or is it all the same because it's in series? It is the same. You're not allowed question marks anymore. Dang it. Confidence. All the same. So I'm going to race. I'm going to have one chunk of current here, one charge, going to trace it here, and one charge here. They both go. Ta-da, now they're there. When that first charge arrives, it's going to put a plus here because it brought a plus charge. And this one goes here. It leaves a minus behind because we lost a plus. So the charge building up on this plate will equal in magnitude the charge on this plate, just opposite signs. Because there was no charge on the plate, easy to move the first one. But if I want to move another chunk of current, it's going to be harder or easier to move this next one. So this one's going to move over here. This one's going to move over here. A little bit harder, a little bit easier, or the same for this plus to move over here. Why is it a little bit harder? Repulsion on this side, this positive is going to be repelled here, and this positive is going to be held a little more tightly. So you read there's stronger forces holding on to this plus and stronger force repelling this plus. So it's going to flow a little bit slower, fair enough, but it will get there if I push hard enough, as long as I'm pushing hard enough. And then I'm going to do one more. I'm going to push again. But again, now there's two pluses. It's going to push even a little bit harder, so it flows slower and slower. So over time, as I'm filling up this capacitor, does it get harder or easier to fill it up? It gets harder and harder until eventually you get so much charge that the repulsion of the capacitor is going to be so great that it won't let any more charge flow. So it gets completely full. So how much charge you put on this plate, you agree, depends on how much you push. Does that make sense? And does it make sense that it fills fast at first, but slower and slower over time? Okay. I'm going to refer to this as the buffet principle, but I think a better one. Any of you ever been to a Mongolian barbecue? It's like a buffet where people's worst personalities come out. So behavior at a oh man, you got to go to one just to watch people try to squeeze as much food as they can into a small bowl. But it's amazing just to watch people. So is it true the bigger the area, this is the buffet principle in general, how many agree a bigger plate can hold more stuff? A bigger plate has a bigger capacity. Does that make sense? Yep, so perfect. We'll add in that next thing. So that's just the general buffet principle. So bigger plate holds more stuff. So a bigger plate, more charge. Then there's also distance. As the two plates get closer together, can this positive stabilize this negative? And is that actually more favorable? So as D goes down, as you get closer, you can store more charge. So I have a constant for the material, bigger plates, store more stuff, distance. Goes down, they get closer together, you can store more. Okay, is this the same as resistance? Wasn't resistance the same thing? Some constant times area over distance, area over length? Or was resistance backwards? Resistance had it flip-flop. So do capacitors do the exact opposite of resistors? Because resistors are length over area and capacitors are area over length. Are they inverted? So when I add two resistors in series, that's similar to adding two capacitors in parallel. Two capacitors in parallel just make a wider one. So if I know what I know for resistors, can I fake my way through capacitors? By all means, and I'm going to commit to that. Yeah, so the distance affects it in the following way. If I take this negative plate and move it over to, let's say, right here, take the positive plate, move it over to right here, if they're closer together, a negative charge closer to positives and positive closer to negative makes it more stable. More stable means it's a better spot to hold charge, so capacitance goes up, meaning if the distance between the two plates goes down, denominator goes down, capacitance goes up. I can store more. So just like resistors, it depends on how far apart they are and how wide they are, but inverted from those. Okay, so far so good. The charge over time shoots up fast and levels off. The current blows out quickly and then drops to zero. Practically speaking, why would I ever need a capacitor? What is a real life utility of having something that can give you a blast of charge, current for a while, then dies out? Do we ever need stuff like that where we need a big burst and that's it? A big burst and that's it? A starter, to start a car, to start a computer, start anything. When you first turn your computer on, you need big bursts to get everything up to speed, and then you're good. So is that why it's really dumb to try to fix your own device with a screwdriver? Because if you actually tap into a capacitor, can you shoot the charge across it? Okay, just word to the wise. But let me give you a different scenario and see if this makes sense. Let's say, hypothetically speaking, somebody had their heart go into a non-functioning fibrillation state, let's say AFib or whatever it might be. Let's say their heart is just sitting there fluttering in an ineffective way. Okay, is it reasonable for you to go and give them some electronic stimulus to literally shut their heart down in the hopes that their natural pacemaking will kick in and it'll restart itself? What, you mean if it's fibrillating, you're saying just do defibrillation? You mean it's that simple? To avoid fibrillation, you defibrillate? Okay, I'll take your word for it. You seem pretty honest. So I ask you this, do you want to subject them to a long volt or jolt for, let's say, a few minutes, or do you just want a quick blast? I forget which one. Quick blast. So would you hook it up to a battery, which is consistent flow, or a capacitor, which gives you a big blast and then nothing? So hypothetically, this is all being made up, but let's say you were a first responder and you had to defibrillate somebody. Let's say you had your paddles. Does it go right away, or do you have to charge it up at first? You charge them up completely, and then you disconnect the battery here. So now this is disconnected in this spot. And now can you hook this up to a couple paddles that as soon as you touch the body, what happens? That's the sound of it shooting across. You get all that current for a brief moment, and you hope it goes across the SA node, and you hope it shuts it down and they naturally restart. Is it important you put it in the right direction, or does it really matter? I mean, do you hook up one to the knee, one to the ear, either way, right, left, left, right, who cares? Or is it absolutely important because current's going to flow in a certain way? The left and right butt cheek. You don't work well as an EMT. Just a hunch here. I'm guessing you lost that job pretty quick. But yeah, do you want the longest or shortest possible path? Shortest possible path, and you want it or don't want it to pass through the SA node? You do, in a specific direction. So the paddles are set up in a very specific way. Does every person get the same jolt, the same voltage, or do you adjust accordingly? You have to adjust. In the good old days, they used to have to sit there and guesstimate, looking at patient, how much lipid, how water content they were, how hairy they were. All those things factored in. They took a guess, they put a voltage. If it didn't work, they turned it up a few notches, do it again, do it again. Nowadays, our paddles automatic. When you put it on there, does it send a test signal across to see how conductive they are and then adjusts? So how many have ever noticed you put the paddles on, it reads it, it tests how conductive they are, and then it sets the voltage either up or down, and then it says good to go. And as soon as it's good to go, I think, and I admittedly, I've only seen this from watching awesome shows like and like, what is it? Light black anatomy, dark white tan, gray anatomy. Watching those shows, they always paddle somebody. It makes for great TV. So within that, I forget. I think once they're about to be paddled, everybody hugs them, right? What? You don't give them a hug? Next thing you're gonna tell me, this is crazy, but you're gonna tell me if you're with somebody who's about to get tasered, you should always hold their hand to show them you love them? Yes or no? Why not? Yes, there you go. Elton is the only one who understands love. So problem is, if you're touching somebody who's getting charge run through them, are you part of the circuit? Do not hold hands with somebody getting tasered. Do not hug people getting defibrillated. The current has to go through the shortest possible path, but it will go through other paths. Okay, fair enough. So hopefully these things seem okay. So weird question, do they shave people and or like put the pads on and rip hair off, maybe go Brazilian for lack of a better word? Why? You want to look good for your defibrillation? Better contact. Two things, you want little hair and as little moisture as possible, so you get a direct contact on the skin to get as much current going into the tissue and across that pathway as possible. So hopefully, does this make sense that a capacitor is used for a big blast? That is one thing, any big blast. So would there need to be a capacitor in a pacemaker? Does a pacemaker give continuous stimulus across the SA node, or is it pulsed? It's actually a pulse. Every 80, 90 times per minute, it's going to give a pulse, a trigger, a trigger, a trigger, a trigger. So it must fill, discharge, fill, discharge, fill, discharge repeatedly over and over, but the discharge is one big blast. So your pacemaker, that little disc that you see on somebody's collarbone, is typically the battery and a capacitor, and they have leads that go into the heart, into the SA node, and it sends a signal at a certain timing. Is it a variable resistor or is it a permanent resistor? Weird sort of question, but hopefully you can make some logic out of it. You have a resistor there, but why do you want it to be variable? So let's go back to a resistor. A resistor drains energy, we mentioned that, but the other thing it does resistance change how fast current flows? If I were to put a resistor in here, is it going to fill slower? If it takes longer to fill, is it going to be more time before the next signal is released? Fills up, then discharges, fills up and discharges, fills up and discharges. Why would you want to take longer time or shorter time when filling with a pacemaker? Doesn't the pacemaker always put out the exact same? Don't you want your heart to always be 85 beats per minute? What? What do you mean no? It adjusts the stimulus. So you agree sometimes the heart rate has to go higher, sometimes it has to go lower. So if the heart rate has to go up, you want less resistance, so it fills faster, discharges sooner. If you want the heart rate to go down, resistance goes up, fills slower, discharges less often. So does that make sense that you would get a resistor that is a variable resistor, not a constant resistor, but a variable resistor you can adjust depending on whether you sense acetylcholine or whether you pick up adrenaline levels or O2 levels, CO2, whatever normal signal triggers your heart to change, the pacemaker has to process those same signals. So this is me being really physio ignorant, and you've asked a question that's beyond my pay grade. So I'm going to backpedal and say the answer is I know, and you tell me how that fits there. So does the pacemaker have biofeedback? By all means. So adrenaline levels, like mentioned, CO2, O2 levels, by all means. Are those the things that are sympathetic or parasympathetic, those feedback? Then I would tend to go with that, because it has to be able to read the exact same things your heart would normally read and adjust it accordingly. Oh, it is so amazing. The pacemaker is so freaking genius. Medicine is genius. I mean, there's so many cool things, but it's basically a capacitor hooked up to a battery with some leads coming out. And one of the things that's going to happen when you go to doctor school, when you go through anatomy, physiology, you're going to work on cadavers. And for whatever reason, a lot of the cadavers have these thick wires coming from their pacemaker into their heart. Very thick wire. Why do you want these wires, these leads that go into the heart? Why would you want these to be very thick? Does thickness affect anything in terms of circuitry? Wider pathway, better current. You agree you want these as low resistance as possible because you want the current to be shot across as quickly as possible. You don't want to slowly electrocute them. You want a big blast. Capacitor gives a blast, wide wires, shoots it across very quickly. So the stimulus is just there for a moment. Cool. Hopefully this seems reasonable. Yes, everybody read what Stephanie put there because it is so annoying and disappointing. So yeah, notice I'm a chemist and I keep going like this, and it's bothersome because you're absolutely right. Current is flowing this way and current is going to go through this. Because I'm teaching a physics class, I need to get over my chemistry tendencies. And you're absolutely right. This is the flow pathway of current. This is the reality pathway of electrons. And so it's just so annoying. Yeah, I seriously apologize. Your crisis moment is brought about my being a chemist faking his way through a physics lecture. And you're absolutely right. Current's flowing this way, such, and that's the way we have to look at it. Okay, QVC, the Q, the total, and by the way, what's the letter Q stand for? Charge, of course. Voltage and capacitance. So I'll field the question. Somebody asked about the larger wire. Let me field that, and then I'll go back to this. Just like everything, if a road gets wider, it can carry more cars. If a pipe gets wider, it can carry more water. If a wire gets wider, thicker wire, it can carry more charge. So in other words, less resistance. I want to control how fast I fill the capacitor to actually control the rate. But once the capacitor discharges across the SA node, so let's say your heart is here. That's an accurate heart drawing. And they would actually be probably somewhere up in there that they'd want to connect or not connect, get close. I want this charge to go as fast as it can through here, shoot across, and return. So I want this pathway to be as fast as possible, making the wires very, very thick. Thicker wires allow for fast transfer current through here. And then this is where I'm going to slow it down up here when I fill. So once it's full, discharge, full discharge, full discharge, but it fills fast or slow. That's going to actually be the pacing. Okay, Mongolian barbecue principle. So the buffet principle taken one step harder or higher. If you've ever been to the Mongolian barbecue, there are two types of people. How many have seen the grinders, the grunt people, the people who try to get as much food in that bowl as possible by pushing really, really hard? How many have ever seen that? Like the elbow people, the bowl smashing people, the palm people, whatever they are, they push really hard to crunch. Yeah, and not to judge, but that's a pretty primitive, I guess, kind of Neanderthal sort of way to do it, even though that's exactly the way I do it. There's a second route. How many of you have seen the more artistic people basically start weaving a basket? They take that bowl and they put their broccoli spaced just the right way, or they put whatever, so that the vegetables form like a net, and then you can put more meat in the middle. Anybody ever seen that person? The person who increases the size? They're rare, but yeah, they're definitely, you don't see them. But yeah, the Mongolian barbecue meta rolls. But you either make it bigger to hold more, or you push harder to hold more. Simple rules. So, but basically, the amount of charge on these plates, if the battery gets higher voltage, we push more on. If the plates get bigger, we put more on. So the total amount of charge you get depends on how hard you push or how big the plates are. So I agree. Crush it in there, you get more food, but also you can make the plate bigger. Hopefully this equation seems okay then. So I want to mess with you one more time. That's my job satisfaction. Oh, this is just a really strange day in terms of my computer abilities. Huh. I don't have the excuse of too many devices nearby either. Yep, okay, I just have to start all over because it booted me. So my iPad hates me. Apparently hates you as well. Okay, so we're good on this one. Okay, here we go, finally kicked in. There's a term called a dielectric. I just want to get this out in the open. This could be a TGL moment coming up. But I'm going to tell you dielectric and dipole are the exact same thing. They mean the same thing. Okay, would that make sense? To have two totally different words for the same thing? But then again, science doesn't always make sense, so maybe. So I'm going to tell you how it works, and then we're going to see if I lied to you or told the truth. If I have this, so before I hook up the battery, let's say right now, it's an open circuit. So how many can see it's connected there, but it's not connected here? So I have a dipole in the middle. As soon as I close this circuit, what's going to happen? Charges will build up in the plates. And will the dipoles line up? Sure. When they line up, the pluses will go to where the minus plate is. The minus will go where the plus plate is. Does that mean that I'm still going to have 5 minuses, or is it 5 minuses and a certain amount of plus to cancel it out? It'll be 5 pluses, but a certain amount of minus. Meaning, how many agree this plate actually feels more or less charged now with the dipole nearby? I guess net charge, I should say. So the 5 minuses are some of them going to be canceled by these delta pluses on the dipole. So as a result, instead of being -5, it might only actually feel like a -2. might only feel like a +2, which means, is it possible that more charge could actually migrate over? So can I actually stuff more charges into here because the dipoles help stabilizing it? So does the addition of a dipole in here increase or decrease the capacitance? Increase it. So really the actual true capacitance is going to equal something called the dielectric constant times C naught. So this really over here is C naught in a vacuum. And then this is the vacuum times whatever it adds. So I'm going to start giving you some values and you tell me if these make sense. For CH4, would you consider CH4 to be polar or nonpolar? Nonpolar ends up, it's around 1.004, meaning whatever you take here, multiply 1.04, and that's capacitance. Does that seem reasonable that it barely makes it go up? Dielectric constant is essentially nil. So 1 means it breaks even, just like a vacuum. Water at different temperatures will fluctuate, but I'm going to tell you it's around 78. Which is why when you drop your cell phone into water, is that a really bad thing? Because it screws up all your capacitors, and it also starts dissolving some of the intercapacitor material. So water for electrical devices, horrible because of that right there. Okay, but would this make sense? Water is highly polar, so would it make sense it increases the amount of stored charge you can get? So what about benzene? This is the one where I want you to make a decision for me. Benzene would have a high or low dielectric constant. What's your gut feeling? Low, so give me a number. Throw a number out there. Okay, so by the way, it can never be lower than 1. If it equals 1, it's a vacuum. So dielectric constants have to be higher than 1. 1.0 means nonpolar, 78 means polar. Is benzene polar? No. So would it be closer to 1 or 78? My initial guess is around 1. And so I test it out. Oh my gosh. And I find that I'm way off. It's actually 3.8. How the heck did that happen? Well, it happened in the following way. What is the right answer to everything in OChem? Resonance. You nailed it. So the resonance that normally would be like that now turns into this. Benzene, when you put it in the field, does it now have an induced dipole? Normally, it is completely nonpolar, but the minute I put it into electric field, does it suddenly become polar because of resonance? So the difference between saying dipole and dielectric, a dipole is always a delta plus delta minus. A dielectric is sometimes it's always, sometimes it's induced. So a dielectric is anything that can have a dipole in an electric field. So benzene is inert and nonpolar normally, but in electric fields, does it become a dielectric? Meaning, does it have a dipole as soon as you put it in electric field? So the difference between the word dipole and dielectric is simply saying whether it's permanent or induced / permanent. Does that make sense, that difference? Why we use 2 different words? So going back to the original thing, when I said dipole and dielectric are the same thing, did I lie? Did I kind of tell the truth? Is it sort of that hybrid? OChem in a physics lecture. Got to happen. It's sort of that hybrid? Exactly. So dielectric. Now, one thing that I really want to bring up, because it was a sort of a toxic piece of information, you may have been told somewhere that if you did gel electrophoresis and you add a dielectric, that it goes faster. And you should ask yourself, if you add something that reduces the plate charges, what's going to happen? Faster or slower? So if you add something in, reduce the plate charges. Now, there's sometimes we put charges in there to piggyback with what we're migrating, and there's other things that go. So there's a whole bunch of specialty things we do. But in general, if you add a dielectric and you do not let the voltage go up, so if all I do is add a dielectric here, and I have it on a fixed voltage cap, it's not going to help it migrate. But if I set it up so it can build up higher plate charges, then it can migrate. Hopefully that makes sense. So do not blindly say, if I add a dielectric, it goes faster. Make sure you understand what's going on in this. So if you just add a dielectric and there's no adjustment, things will migrate slower. But if you have an adjustable current, adjustable voltage, then you can do it. So there's specialty things. I'm going to leave it at that and leave that for another lecture. But hopefully this makes sense. So onward we go. Capacitors then. Sorry for the lack of a heads up on that click. Sorry. Yep, it'll initially lower the charge on the plates, and ultimately the plates will fill back to their normal like perceived charge, and in doing so, increase the amount of stored charge. So dielectric is defined as something that will increase the amount of stored charge in capacitor. Okay, circuit elements, capacitors. In series, they screw one another up. This plate starts taking that plate's charge, so the total capacitance goes down when you hook them up in series. In parallel, it's kind of like if you went to the buffet, would you put the two plates, if you got two plates, would you put them side by side or stack them to maximize your buffet experience? Side by side, because they add to one another. To be stacking would be silly. You'd waste a lot of perfectly good plate space. So hopefully this seems okay. And again, parallel, same voltage drop, series, the same current. Okay, circuit elements down pat for the most part. The rest of it, gonna mess with you. For now, things I need to note then. These are just things that I hate to use the word memorize, so I'm gonna say, don't memorize these. Instead, write them down and look at them for a really long time until you remember them. In series, same current. Parallel, same voltage drop. Fair enough. Make sure I understand what this means. If I told you in this picture I had currents of, again, I don't understand the lag time of what's going on here. There we go, finally it kicked in. Okay, so for these two, if I told you we had currents of 2 and 4, would you say, yep, I believe you, good call, or no? What's wrong with that picture? Why do you say no? They should be the same. You should get the same current because whatever current goes to one has to go through the other. They are in series. So you're not having anything taking a shortcut or a roundabout, they have to go through. So if I told you they were 3 and 3, would you believe me? Okay, perfect. Okay, so you get the same current. Tell me the difference in this sentence. You get the same current, you get constant current. Is there a difference between those two sentences? Yes, the same current means whatever the numerical value through one is, it's the same through the other. Constant implies it never changes. Exactly. So if I have these same two and I add one more resistor in series, I tell you they all get 3, have I just designed a system that has the same current or constant current? At face value, it looks like the same, but I've made an error. I mistakenly thought same as constant. When I add another resistor in series, what happens to the resistance of the entire circuit? It increases. If the resistance goes up, what has to happen to the current? It has to go down. This is actually wrong. I would get a situation like this. I'd get a situation where they'd all would now have, let's say, 2 amps. They all have the same current, but it's different than the previous current when there were only 2 in series. So as I keep on adding another resistor in series, does it diminish the current through the other resistors? So in this case, I was fine, but when I added this next one here, did it reduce the current that the other ones were getting? Yes, they all have the same, but they all share the diminishing amount the same. Hopefully it makes sense. So by same current, we simply mean in a series pathway, every resistor gets the same current. Yeah, it just bottlenecks it. So anytime you're in a line and let's say you have to go through two checkers, you have to go through one that checks your ID, the other one that checks to make sure you are clear to purchase that, and then the person who makes you pay for it. Is that going to take it more or less time than if you only go through the person check and pay and checking if you have ID? Every time you add another step to the pathway, does that screw everybody up in the line? So in series, think of it like check stands you're going through. One bottleneck here affects everybody downstream. Every extra checkpoint makes it take forever. So if you've ever gone through like clearance at the airport when you go to another country, would you agree every single thing you have to stand through makes it worse and worse? Good question. Define time. On our time scale, it will feel pretty instantaneously. But reality is, no, it takes a few nanoseconds to milliseconds, depending on what it is, for it to trickle back. So I'm going to say for NCAT purposes, yeah, on our time frame, what we can relate to, it's instant. But in reality, no, the bottleneck has to slow everything down. So in reality is, it's like there are microprocessors that do worry about that sort of thing. We're probably not going to worry too much about that. Okay, that said, parallel, is this okay? Could you have two different currents in parallel? Yes or no? Sure, perfectly fine. If I add another one, can I have three different currents in parallel? Can you have three different devices plugged in to the same out or same source and have them all run independently if they're in parallel? Yep, you bet. It starts draining this, and eventually, if you put too much current in parallel, do you eventually screw the circuit breaker over here? Yep, exactly. I'm going to say same voltage, but yeah, exactly. Depends on the R and the voltage. The voltage is the same. So different R's, different currents. Path of least resistance, this one. Path of most resistance, that one. How do I know? Lower current. I'm going to go out on a limb and I'm going to tell you R1 is 3 times as large as R3. Do you believe me? Sure. Because if it's 1/3 of the current, it's 3 times the resistance. And yes, to answer your question, same voltage drop for all of them. Exactly. Okay, clicking on, different voltage drop in series. They each take a little chunk of the voltage. Here you get different current. Path of least resistance gets more current. If you add two things in series, the equivalent resistance is going to go up, meaning R1 plus R2 plus R3 plus R4 gets bigger and bigger. When you add them in parallel, every time you add a new one, you add an extra pathway, makes it easier for current to get through, resistance goes down. Voltage, the exact opposite. Capacitance, excuse me, the exact opposite of resistance. The big thing, this equation, they all work. The power equation is defined as power equals IV. By manipulation, we make it I squared R or V squared over R. They're both the same thing, but this would be the preferred equation for comparing two things in series, because if they have the same current, then power simply is going to fluctuate with the resistor. However, in parallel, why is this the preferred equation? They have the same voltage, so again, only depends on resistor. We have to do that. So I want you to do a thought experiment for me. I'm going to have water flowing this way, and I'm going to big paddle wheel and a small paddle wheel. And the water's going to flow. Oops, sorry. Is water going to flow the same rate because it's in series? It's a river in series. So which one is going to give me more energy? A big wheel spinning or small wheel spinning? Which is going to actually give me greater energy? Big wheel will give me more energy. More E, they spin at the same rate. But now we get creative. and we split the river up so the water can go both ways. So now I have a slow spinning and a big spinning. I should say fast. Let me say with accurate adjectives here. Fast spin because I get more current this way, more flow. So which one's going to generate more energy? A slow spinning big wheel or a really fast spinning small wheel? Initial thought would be same. It ends up, this one gives me more energy. So if you turn a big wheel really slowly or turn a small wheel really fast, you actually tire out faster if you're turning a small wheel really fast. And that's just, that's what we're trying to get at here. So more energy in this one, here the small one. So with series or parallel unit with different energetics. Okay. One last thing, I'm gonna have to erase this absolutely beautiful artistry I've done. So it's erasing in 3, 2, 1. Done. Oh no, definitely we're going to get voltage, current, and resistance. They can give you any of those. And so for voltage drop, there's going to be a question popping up where that's exactly what we're going to have to do. We're going to have to look at voltage drop. But yep, they're free to screw with you in any which way. Your job, don't get screwed with. What's meant by dependent and independent? I don't get what that means, so explain that to me. Dependent. If one breaks, the whole thing breaks. One depends on the other, depends on the other. Here they're independent. Unplug your toaster oven, doesn't change anything else in the house. Trip your circuit breaker, and it screws everything. Okay, screenshot if you will. I'm clicking in 3, 2, 1. Last but not least, voltage sources. We mentioned again, Fat Cat, Little Orphan Annie. Current flows alphabetical. So where do I have the greatest potential to move? Cathode or the anode? Where does current start? Current starts at the C. So the C has high potential to move because the current's going to move away. Currenta, perfect. But when it gets to the anode, what's true? Does it keep flowing or does it stop at the anode? Stop. So once it gets to the anode, does it have any potential to move anymore? Nope. So we say the capacitors at high potential, the anodes, or cathode, excuse me, at high potential, the anode at 0 potential. It'll flow around the circuit. When it gets to the anode, that's the end of the line, meaning voltage will go from high to 0, which means over the course of a circuit, does the voltage stay constant or does it drop? Drops, exactly. Potential to move. This is the common one. If they mess with you and put this on there or this on there, they don't want you to go into any detail other than recognize it as a voltage source. AC, they might do it to mess with you. They might convert AC to DC and give you this. How many would freak out at this mustache or sine wave gone wrong? Or this coil, this slinky stuck in the middle of my circuit? The rule is this: if it's not a capacitor, not a resistor, it must be a voltage source. This is the most common way you'll see it, but they have been known to put on a few weird things from time to time just to make your life miserable. Don't fall for their trickery. It's not a capacitor, not a resistor. It is something that makes the voltage go, something that makes the battery work, the circuit work, excuse me. Ohm's law. Oh, where does the voltage go? I don't know. So when you go upstairs, do you have less potential to move as you get up there? It goes into actually moving you. So as something flows from one point to another, it's just dissipating its voltage and energy as it goes. So I'm tired, I don't want to flow anymore. I reached the end of the line. So your desire to get to here is getting less and less and less along the way. So voltage drops, power drops. Ohm's law. Oh my. So Ohm's says all the voltage you have here is lost by the time you get here. So this is known as a voltage drop. VIP, you're powerful. If you're a VIP, voltage times current equals power. Can also be rewritten as plugging in IR for V, making I squared R, or divide both sides by R, V over R equals I, so plug in V over R. So if I plug in R for this, I get I squared R. If I plug in V over R, I get V squared over R. Which equation is the one that's correct? This one, or this one? Exactly, all of them. They all should give you the right answer, but is one going to be easier to use than the others based on what variables you get? Sure, so we're good on this. Okay. Kirchhoff's loop rule. Everything is lost by the end. Okay, again, and I need to apologize every time somebody asks this because I can't explain why physicists and chemists do this way, but anions go to the anode, cations go to the cathode. Where? This is totally true, but where is this happening? So where exactly does that apply? To the wire or to the field? It applies to the field. Cations will go to the cathode, anions will go to the anode. So let me do that in two different colors to emphasize two different thought processes. If I'm doing electrons, electrons flow there, anions go across, electrons flow there, I have a negative loop. If I have current, the flow of positive charge, I have a complete flow of positive charge. The anions go to the anode, cation goes to the cathode. I care about for this part here where we do electrophoresis, the field. As far as the wire goes, anions, electrons flow alphabetical, anode to cathode, current flows currenta. So for the wire, I care about currenta or alphabetical electrons. I only apply cations, cathode, anions, anode in the electric field portion. Doesn't on the wire. Because what you just asked is kind of like saying, well, aren't electrons like anions and aren't they going to the cathode? So think of two different pathways, the wire and the field. Anions go to the anode, cathode goes to the cathode, only works here because where do you do gel electrophoresis? On the wires that are plugged into the wall or in the gel between? In the gel, exactly, the field. So in the field, cations go to cathode, anions go to anode, everything else is wire related. And again, I don't know why I feel compelled to always have to apologize for the way they came up with this, but because physicists and chemists have opposite rules, how many agree this is just confusing as hell? That it's just like, why can't they just get one system? They have two, we have to know two. And so keep in mind, current and electron flow is through wires. Ions, charged species migrate through fields. It is so confusing. And it's actually, angering is maybe a strong word, but I just like get frustrated. Like, why do they have to do it that way? But you know what, they do, and I'm okay with it, and we move on. I hope it makes more sense now. And again, the key thing, remember your field is for ions and wires carry charges. So even though that's a weird sentence, it's an empty sentence, but it's true. Okay, erasing this in 3, 2, 1, and done. Can I quote you on that for everybody and see how many agree with that? How many agree every time you do it, your brain hurts? Does anybody feel that way? Like, damn, this stupid thing again. Yeah, isn't that weird that chemists and physicists never got on the same page because one worries about the chemicals in the flask, one worries about the energy outside the flask. That's the only reason we have no consistency, and neither will give. And it really comes down to a friggin' negative sign, and nobody will give on it. But it's the way it is, and it is what it is. Oh yeah, they're both sciences where you name things after nature, life, or yourself when you discover it. All of them could take a big hint from bio where you name it after what the enzyme does. So I'll bet you can't name any of the people who discovered the various enzymes, but all the things in chemistry and physics. So at any rate. Okay, within this, high voltage, zero voltage, we call it a voltage drop again because we lose it. V equals IR. How many have this programmed in? The greater good. You sound like a Harry Potter movie. That never works. Caring about people. Okay, V equals IR, voltage drop. So let me get rid of what I've written. And if we have a system here, let's consider what happens. If I have 12 volts coming out, if it loses 4 volts, then I have 8 volts left. This pathway loses 8. So by the time I get over here, we have 0. So each circuit element, in this case 2 resistors, is going to drain some of the voltage so that by the end, all the voltage is lost. In parallel is the kind of the weird one. We have 12 volts coming out. We get to a junction. We have a choice. Ends up 12 volts goes up top. If 12 goes up top, 12 has to go below. We lose 12 in each, so 0 ends up 0 in here. In this case, parallel have the same voltage drop. Each are 12, but they can have different currents. In series, they can have the same current, but notice they get different voltage drops. Just stuff you end up having to memorize. And then my personal favorite, the junction rule. The junction rule is as follows. What goes in has to be accounted for. If 10 cars go into a junction, let's say 6 of them take one pathway, let's say the pathway to the left, 4 will take the pathway to the right. If 7 liters of water go in, if 6 liters go one way, 1 liter goes the other. If 10 amps of current goes in, if 8 amps go one way, 2 go the other. Do things split when they get to a junction? Some go one way, some go the other. When they come back together, do we have all the cars, all the water, all the current? Everything's back. So how many learn this? That what goes in equals what comes out, and in between, they split themselves up. So it makes common sense, works for everything. Oh, it is so from forever ago, maybe even longer. So this is back when the Earth was flat. So let's consider this. Help me out with the junction rule. If 6 amps go in and the upper pathway gets 4.5, can you tell me how much the lower pathway gets? Perfect. So I get, in this case, 4.5 amps. So do you agree 1.5 amps? Because they have to add to 6. And then how much voltage do I have through the upper path? .5 times 2, 9. So 9 volt drop. So how much is dropped through the lower path? 9. Perfect. So 1.5 times 6, current is 1.5, resistance is 6. Notice, again, the resistor is 3 times as large, the current is 1/3. Because V equals IR, the product of IR is the same for each. If you have double the resistance, half the current. You have 3 times the resistance, 1/3 the current. 10 times the resistance, 1/10 the current. Hopefully this makes sense. And if it does, question time. So they give me this complicated circuit that freaks me out. Current is going to leave the cathode. When I get to over here, what happens? Does it split between the two? It comes back together. Everything passes through here and splits again, comes back together, and then reaches the anode. So can you fill in some of the blanks on this table? So how much current is going through I2? What's your conclusion? Oh, because why is it negative? It isn't that I is negative, R is negative. It's that it's a voltage drop. So just by definition, if we have 12 to begin with, if the voltage drop is 6, then we say it's a -6 across that. So it's just to define the fact that it's lowering the total. So negative and positive don't mean much when it comes to the sign or the quantities. So How much current do we get through this one? How do you get that, Iman? Perfect answer. Ah, perfect. Because current goes in, it splits up, then comes back together. So how many agree R3, whatever current is going through 3, is all the current? Goes, splits up, comes together, splits up, comes together. So if this one was 3, and this is 8, that must be 5. So can you guess my next question before I ask it? If that's 2, perfect. Okay, so first question out of the chute. From trial 1 to trial 2, did the voltage go up or down, first off? Up. Why do you say that? Because the current went up. So if the current's faster in this one, it was faster in everything. So the voltage had to go up, perfect. By what factor? 1.5. Do you agree 7.5 over 5 is 1.5? So best answer. B is in, boy, you nailed it. Okay, now if we had a trial 3, where the voltage is now doubled, that means 6, 10, 16, 4, and 12. How many are okay with that? The voltage, V equals IR, V is doubled, all the I's are doubled. So what's your best answer? D is in, damn, would they really make me do it that way? Is that a realistic type of thing for them to do on a passage? Give you multiple trials of the same thing? You bet. This is right up their alley, which how many in the beginning are stressed out, but when you see the answer, it's not so bad? More than most subject areas, confidence. Yeah, when you double it and draw it out, it's easier. When you put the numbers in and bookkeep it. But how many agree this is one of those things where confidence is a bigger thing than the actual content? So how is trial 3D? The following way. So what they told me in trial 3, we doubled the voltage from trial 1. So if I double the voltage, V equals IR, double the voltage, I'm going to push twice as much current out. So instead of being 3, it's now going to be 6. Instead of being 5, it's now going to be 10. Instead of being 8, it's now going to be 16. Instead of being 2, now 4. Instead of being 6, it's now going to be 12. And then, yeah, so R stays the same. Exactly. We didn't change these. We only changed that. So these all stay the same, but double the voltage pushes double the current. So I2 is 10. And I5 is 12, according to this. R is constant, exactly. Hopefully seems okay. Oh, Elton, way to be on top of that. Were you afraid I was going to yell at you again? In a passive aggressive way? So hopefully it seems okay. So is that alcohol, office hours, or, oh, it's now making sense. Oh, no, yeah, I'm sorry. Yeah, D of this one. Perfect. Okay, free to move on. Screenshot if you need. 3, 2, 1. Give you about 30 seconds to do this. Oh, I'm so glad to see answers. This is downright mean to me, because how many are trying to do math? The problem with physics is most physicists make it a math class. I'm going to try to avoid math if at all possible. So let's go ahead and draw the system. How many amps are going in, according to this question? 12.3. So let's just pick choice A, because at first there, if 12.3 goes in, it's got to split up. So would it be reasonable if choice A were correct, 12.3 here, that means 0 and 0. So is that the way circuits work? Lowest resistance gets all of it, everybody else gets screwed? Or does it get split? It gets split, not equally, but it does get split. So if we can get rid of A because one path isn't going to get everything. Okay, let's go to the communism approach. Everybody shares equally. Is that the way it works? Do they all get 4.1? Or is there a path of least resistance? Nope. So this one won't work. So can I get rid of C as well? So is this one going to get a little bit more than a third or less than a third? More? Less? Please don't ask me. I'm so afraid, dear test writer. A little bit more, a little bit less, and a little bit of And that's how many go through that same mentality. Thank God they didn't ask me this one. Kind of the way it works. So the best answer then, more than 4.1, this. If they would have asked for this one, B would have been my best answer. I think it's easier to conceptually, but yeah, there definitely is. If you want to do this mathematically, by all means you could. To do it mathematically, current will be the following. So for this resistor here, voltage drop across that resistor. I'm just not even going to drop. V would equal IR. So I know that's 2. All I got to do is solve for V, and I get R. The voltage is going to be the following. This amperage here times the equivalent resistance here will equal voltage of the battery going in. So I'm going to come up with voltage of the battery equals 12.3 times R equivalent. So all I gotta do for R equivalent is 1/2 plus 1/4 plus 1/6 and solve for it. Get that number, plug it in here. That number is going to be a little more than 1. So it's going to be a little more than 12, so around 14 or so, 13. Then take that number, plug in here, and divide by 2 and get that one. And it's easy after 3 months. How many agree? Yeah, I could do this with unlimited time. Totally doable, completely totally doable. And unfortunately, how many is that your natural pathway to go down because that was how you did physics? The problem is in school, it was always a math class. Given infinite time, that's my solution. Pragmatically, is this a better solution? Path of least resistance gets more current. Yep. Oh, given infinite time, anything is possible except for time travel. Sorry for a weird thought like that, but hopefully this one seems okay. Ask away.
Okay, so I just got home from work, so I'm a little late to the party. But so if I'm understanding it correctly, the number before Q, that's your voltage, right?
Oh, this letter right here is
not
this one
Q,
right here is,
sorry, that's just the
whatever it is. Ohm, it stands for ohm, it's omega, but it's a resistor quantity.
Oh, the resistor quantity. So if it's the lower the number, the higher the voltage on that?
No, always the same voltage. In parallel, you always get the same voltage drop no matter what. So the voltage, whatever it is here, is here, is here.
So then what are we saying? Like 4.1
so voltage equals
is higher with the 2 versus the 6.
What's so big question. What is A the unit of? Is A the unit of voltage, resistance, or current?
Current?
Current. A is for amps, exactly. So the current. So what do I get when I multiply current I times resistance R. IR equals voltage. Perfect, exactly. So one of the things we mentioned earlier, so probably you were probably somewhere on the freeway when we mentioned this, but assuming you can be in a freeway, but whatever it might be. But voltage here equals voltage here equals voltage here. In parallel, you always get the same voltage. Just one of those things to hang on to for memory's sake. So if they all get the same voltage, that means they all have the same I times R. So if it's a smaller R, you get a bigger I. So the current is more than 4.1, around 4.1, and less than 4.1.
Okay, got it. Thank you.
Hopefully
I just
okay.
confused myself.
Yep. But hopefully it makes sense in terms of the junction rule and then path of least resistance getting more current.
Got it.
Okay. You're welcome. Equivalent resistance. Again, you have 10 seconds to get this right. Oh, get home safe, or I think she got home safe, didn't she? Or are you yelling at her?
I did. I got home safe. I'm here now.
Okay. Yeah, you're living in the past, Jonathan. Let it go. Move forward. Okay, what's equivalent resistance for this? Perfect. How do you guys get it so fast? Product over sum. Exactly, our shortcut. 2 times 3 over 2 plus 3, 6/5, 1.2 ohms. Okay, depending what they give me. If they give me a circuit with all resistance, I'm going to do it that way. That's nice and easy. But what if they give it me a little bit differently? What if they told me it was 6 volts, and the equivalent was 1.2 ohms for both of these? Then I could solve it the other or different way. The total voltage and the equivalent resistance tells me the total current. So the total current leaving here, do you agree, is going to be 3 plus 2 amps according to this method? And how the heck did I come up with 3 and 2? Where did those numbers come from? V equals IR, exactly. 6 volts, no voltage lost here. There's no circuit element, no voltage lost here. So all the voltage is lost here. So 6 volts, 2 times 3 is 6, 3 times 2 is 6. 3 plus 2 equals 5. I can also get it if they gave me the amps. 3 plus 2 would be 5 amps total. Resistance equals 5, or equals, sorry, V equals IR, so V equals V over I equals R. Whew, can't just actually point to letters and say it. Because V equals IR, V over I equals R. If voltage was 6, and they told me these were 3 and 2 respectively for 5 total, could I solve for R equivalent that way as well? Basically, let me just catch my breath and say, if they gave me the resistances, I can get it that way. But if they give me a different question where they said 6 volts, 3 amps, and 2 amps, and asked for what the equivalent resistance is, could I also solve that question? So in other words, can they give me the same circuit and ask me the same thing 2 different ways? Directly or indirectly? I equals current. Yeah, it's not you confusing yourself. It's physicists' really crappy dictionary where letters don't match anything. That's what's messing everything up. So I is, of course, I is the first letter in the word current. Come on, everybody knows how to spell that. Just like, what's the first letter in the word magnetic? B, of course, exactly. And charge begins with a Q. It's us. I apologize on behalf of all physics spelling in the world. It's screwy. And so there's an extra layer of confusion and learning just to get past their variables. Okay, the amp value again, 2 ways I get it. One equation is V equals IR. And so across this, if I have 6 volts and I have 2 ohms, then what does I equal? Is it 6 divided by 2 or 3, if that seems okay? One way to get it. The other way to get the amps is V and R, or splitting it up. If I have 5 amps going in, then because the resistors are in a 2-to-3 ratio, the currents have to be in a 3-to-2 ratio, exact opposite. So 5 has a split in a 3-to-2 ratio, which is kind of V equals IR, but splitting it up. So 5 goes in, path of least resistance gets a little more, path of more resistance gets a little bit less. but they still have to multiply. 2 times 3 has to equal 3 times 2. Hopefully it seems okay. Okay. My goal, I want to screw with you. Oh, you're welcome. So I'm going to add one more resistor in here. Let me erase everything. Is this parallel or series with the other two? Parallel, meaning it's dependent or independent of these two. Is it getting its own private path? So let's figure out what that means. Dependent versus independent. If it is dependent, that means if this breaks, the whole thing breaks. So if I disconnect this one, degree, there's still pathways here and here. It is an independent pathway, meaning does it get a different voltage or the same voltage as the other pathways? Same voltage. So what is the voltage across this pathway? 6, just like the other one's got. So if it's 6 volts and 6 ohms, how many amps do I get through that pathway? 1. Perfect. So when I add in one more circuit element in, plug one more thing into my outlet, even though it's in parallel, did I just put the demand on the circuit breaker higher? Instead of a 3 and a 2, is it now a 3, 2, and a 1? Does it now have to generate, instead of 5 amps like before, does it now have to generate 6 amps? So doing it the old-fashioned way, the red way, I would get the voltage is 6. The total current, 3 plus 1 plus 2 is 6. So 6 over 6 will be 1 ohm. If I wanted to do the new shortcut way, remember, I cannot do the sum of all of them over the product of them. I have to do them 2 at a time. So you said earlier, the 3 and the 2 were product of 6 over sum of 5, so 1.2. So I would take my 1.2 for the 3 and the 2 times 6 over the 3 and 2, making 1.2 plus 6. I don't know about you, but I think it's so cool that 1.2 times 6 equals 1.2 plus 6. They're both the same number. If it was English, we'd give it some name like palindrome or something silly like that to celebrate, but kind of cool. But the moral to the story, as I see it, are there 2 ways to solve this question? From the currents and the voltage, indirectly, or from the resistances, directly. So the question is, what is the equivalent resistance? If they give me resistances, plug in this way. If they give me everything else, solve for R equals V over I. So my question to you, which is harder, solving it or figuring out what they're asking? Once a math is set up, how many have no issues doing 3 plus 2 plus 1 equals 6 and dividing 6 by 6? I mean, this math might be a little trickier, but the math is not the challenging part. It's what the heck are they asking me? So always go with, they ask for resistance. If they give it resistance, do it directly. They ask for resistance, if they give it indirectly with voltage and currents, and go this way. So it's a matter of recognizing the setup, not so much doing the setup. That's going to be your trick. More complex? What makes this circuit more complex besides the fact that it hasn't shown up on screen yet? Why is this one more complex? It combines series and parallel. Oh, okay, no worries. Take it one step at a time. I'm going to trace it, like they say, you should be able to trace. If I can go like this, do you agree, before I get to this junction and have to make a decision, which way do I go? Am I passing through a circuit element? So is 2 in series with everything else? Sure, so I'm going to say, let's break it into different segments. Pre-junction, interjunction, and post-junction. Pre-junction, I have a 2. Interjunction, do you agree, I have a pathway 3 and 6. Again, 3 times 6 over 3 plus 6, 18 over 9, 2. So collectively, is it 2 for this group? So if I have 2 ohms here going in, collectively 2 ohms here. And how much resistance when there's no resistor here? 0. So R equivalent is going to be the following. 2 for the first segment, plus 2 for the equivalent segment, plus 0 for that segment. So 2 plus 2 plus 0 equals 4, equivalent resistance of 4. How many are okay with doing that? Just breaking up into segments, pathways along the way. Okay, I'm feeling pretty good about this. So now let's trace voltage. Let's say, again, we have 12 volts. Isn't it lemon squeezy? Yeah, dang it. So, you need to just get that stuff straight, dang it. Okay, 12 volts comes in, nothing, nothing, nothing. And all of a sudden, when 12 volts goes from here, am I going to lose some of my current, some of my voltage drop? Yeah, do appreciate that comment. You need some profanity to make it totally correct, by the way, but sounds good. So some of the voltage is going to be dropped here as current passes through this. Then current has to go through here, some voltage drop here. So now to figure out what I get. So if R equivalent for the entire circuit, if all these combine to be one resistor to have 4, what is 12 divided by 4? I clicked way too fast. Sorry. Good answer, 3. So the total current represents the current leaving the cathode and what eventually gets back to anode. So 3 amps goes out from here, 3, 3, 3, 3, 3, 3, 3, and suddenly 3 is going to interact with here. So in this segment right here, 3 amps pass through a 2 ohm resistor. What is 3 times 2? 6. So 12 volts goes in, but I lose 6 volts here, leaving me with a grand total of 6 here. Over here, I have no voltage loss because there's no circuit element. So 6 is here and 0 is here. How much voltage is lost from 6 to 0? 6 again. So 6 volts to the upper pathway, 6 to the lower. If voltage is 6 and resistance is 3, what's the current through this one? 2, perfect. And then if the voltage is 6 and resistance is 6, 1. 2 amps and 1 amp. 3 equals 2 plus 1, check. 3 times 2 is 6, 6 times 1 is 6, so 6 volts here. 6 volts lost in the first part, 6 volts here, no volts here. Yeah, it's just completely mathematical luck that this happened, but yeah, it's just perfect. Yep, delayed reaction. It's called a grenade. Grenade learning. Doesn't go off right away. How many, and I'll be honest, this is probably, again, way too much information, but how many of you get more thoughts done in places like the shower or driving when there's nothing else going on? Because usually it's those spots. I mean, it's just, yeah, nothing else to focus on. Oh, brain is empty in those points. But yeah, it's those grenade things. Okay, good question. How in-depth will MCAT resistor questions be? This is pretty typical. Occasionally, it might be a little more complicated. There's certainly one on the AAMC section bank that's going to punish you severely, but most of them are pretty straightforward. Homework is going to be pretty on par with what they like. Yeah. Oh, the one on the section bank is way more complicated. Some of the homework ones will be a little more complicated, but you keep your things. The thing is, if you keep things simple, they all are this: pre, during, and after junction. But this is a kind of complicated one. Yes, see, that's a good question that you guys can answer better than I can. How many found section bank questions to be harder than practice test and the real MCAT? Oh, 12 has to be given. The voltage of a battery, you have to be told. So this was a given. So I probably should have put that in a different color. You're right, because I solved for the red here, but you had to be given that one. Okay, so no feedback on the section bank compared to real MCAT for anybody who chimes in. Okay, mixing circuit elements. Last one I want to do. No math, just life. What happens with a capacitor? Do capacitors eventually fill up? Yeah, resistor questions are not all that common. You might get a neuro-related one, you might get a pacemaker or something like that, but generally, for whatever reason, circuits, maybe a freestanding question, but usually it's the applications of magnetism or electricity that become more like, I don't know, like how you hook up an EKG, that kind of thing might be more likely. Okay, for this one, when a capacitor is full, you read, is that it? Is that end of the line? Once it gets charged up, it repels. So you get a big blast of charge and then nothing. Big discharge of charge and nothing. They fill, they're done. They empty, they're done. So they only affect it. You have probably experienced this if you've ever lived in an apartment building, but have any of you ever had your lights dim a little bit? Okay. Did it last for a couple of days or just a split second? Just a split second. What happened, somebody in a nearby apartment turned on a device that had a massive capacitor. What happened was they discharged a big blast of current to start whatever their device was, their big screen TV or their whatever, and it sucked, that capacitor sucked all the current for a brief moment, and then you were good to go. And so I'll show what that means in a second. Let me toss these two. So for this one, you were wired in parallel with your neighbor's resistor or your capacitor for just a brief moment. So they're in a neighboring apartment, you're here, you're normally getting a certain amount of current, but when they turned on their capacitor device, did it suck up all the current at first? So your current, you come to here, you have a choice. Do you go through the resisting resistor that resists or this pathway? So when they turned on their device, their capacitor sucked up all the current for just a brief moment. So they had all the current, but then it filled up and it was all done. Then after this was fine, did it get all its current back? So you have a firsthand experience on how long it takes for a capacitor to load up. A couple days, a few months, an hour, or less than a second. Less than a second, way less. The dimming time you felt was the time it took for this to get filled and have no more current to this got all of it. So how do you know that their capacitor was full? What's your test? Your current is back to normal. So let's go back to the AED. Let's say you want to apply it. Does it give you a sound or a light or some indication that the capacitor is full? Sure. So the capacitor is wired in series or parallel with the indicator light or the indicator. In parallel. So as soon as the indicator light is back on, this one must be completely full. Oh, no problem. Okay, thanks for the heads up. Okay. Onward we march then to some questions. So minute and a half for this one, and we'll talk in a second. Okay, so for this one, complex circuit. So let's see how we walk our way through this. How many to start writing things down? So my numbers are 4, 12, and 9. Did they give me resistances, voltages, or currents for the most part when I started? Resistance. So chances are I'm going to have to do the resistance. I have this one isolated by itself, nothing on this pathway. And in here, what is the equivalent resistance of 4 and 12? 3. How do you get that? Math? Thank you. Any particular math? Greatly appreciated, but product 48 over sum 16, 40 over 16 equals 3. Perfect. Nailed it. Okay, so I have a 3 in series with a 9, and now I know there's 24 volts. So there's 24 volts that come in. 3 and 9 add up to 12 altogether. So 24 volts divided by 12 ohms equals 2 amps. So here's what I know then. I know that 2 amps are going to go in, 2 amps are going to come out, and whatever happens here I'm going to ignore for a second, because I find personally it's easier to do the following. What is 2 times 9? 18. So if 18 are lost here, 6 are lost here. So 24 coming in, it's 0 in the end, so 18 lost, 6 is lost. How many did it that way? How many got this and got this one by default? That worked. The other way you get it is 2 amps here times 3 ohms equivalent, 2 times 3, so 2 amps collectively times 3. Yeah, and there's different ways to solve it. So if you didn't do it this way, I did it this way. I don't know why. I don't know why I decided to get the other one first and get this one by default. But if you chose to do it this way, 3 ohms equivalent and 2 amps split, but 2 amps total in the pathway, 2 times 3, you could have also gotten it directly, 6. But how many agree this question was just time consuming? Once it's set up the right way, it's not hard, but getting it set up is a pain in the butt. Complicated circuits, it's going to just take a little bit of time. Oh, see, I was about to comment that is so true. It is so fun. And then you had to shut me down with a JK. So anyway. Yeah, our equivalent was necessary no matter what, because they only gave me ours. So I had to solve it that way. Oh, so how do we get the first way we did it? 6? Because the total voltage when you start is 24 and when you finish is 0. And so if I know that I have 2 amps and 9 ohms, then altogether that's 18 volts that have been lost. So if I have 24 to begin with and I lose 18 there, then by default, what's the other one losing? 6. Yep. But isn't it those things that's a light bulb one? When you see it, it's like, oh, dang. And if you're slapping your forehead, that is fine. That's a growing process. No worries. Yes, exactly. How many read Stephanie's comment? If one's losing 6, the other one's losing 6. Let's just double check. 6 divided by 4 would be 1.5 amps. 6 divided by 12 is half an amp. 1.5 plus a half equals 2. It fits that way. Everything connects, but it's overwhelming. Okay, so for anybody who just had a light bulb, a revelation moment, how many, totally honest with yourself, and with me if you want to be honest, I don't care, but how many have been battling information overload on a lot of this stuff? Too much crap coming in at once, and then all of a sudden when one thing clicks, little by little they all start to click. And that's the circuit moment. If you haven't had it yet, it will come. If you've had it, it's kind of a cool, like, oh my gosh, these are fun, like a puzzle. They're work. This is not easy by any stretch of the imagination, but it makes sense that you can solve it many different ways. Yep, that's it. Stephanie's comment is so spot on that it's like it takes a while to get there, but all of a sudden it's like, ah, yes, I get it. So I'm so convinced you get it that guess what? Clicking in 3, 2, 1. Oh, it's frozen again. You've been saved by my bad computer. Okay. You're going to hate me for saying this, but you should all be done by now. And if you are not, it's because you're trying to make a math question out of all these things. Perfect. Oh, mentally checked out. Okay, I meant differently. Yeah, you got checked in with an answer. How many are trying to do math? How many, when you see physics equals math, start mathing away? As best you can, try to step away from math and make math your second option, your last resort, because noise question. The question was simply this: what is observed if you add a resistor in series? What do you know about adding them in series as opposed to parallel? If you add another resistor in series, does it make the resistance go up or down? So if you add it in series, resistance goes up. So therefore, what happens to current? Current goes down. How many choices give you down? Only choice D. Damn. So my question, do they really do that on the test? Yes, this one was highly inspired. Are they guilty of lots of information that is irrelevant and then a simple question after overwhelming you with too much stuff? They waste your time. Oh my gosh. I'm going to quote you on that one because that is so true. The passage, about half of it is wasted time. And questions, there's at least a sentence or two on every third or fourth question. It's complete waste. Yeah, exactly. If you end up needing the quadratic equation, you have gone down the wrong pathway and are not getting to the cheese. The other mouse is probably eating your cheese by that point. So, next question. Power. Yep, don't fight the power, answer the power, dang it. So just logically, I'm going to ask you. Yep, exactly. So the term drain and drop, exactly right. A voltage drop is where the voltage starts higher, and every time you go through the thing, it's said to step down or lose a little bit. Drain is when the power leaves. Okay, so a few things I want to make note of. If you have exactly half the resistance or double the resistance, depending on your perspective, will that mean you have half or double the current? If that makes sense. So half the resistance, double the I. There's a power equation, so I want you to just estimate for me right now, but is there a power equation I squared R? If this is half and this is double, but this is squared, which is more important, current or resistance? current is more important? So more current, more power. Or the other way of looking at it, how many learned voltage is also important? You get the same voltage here, same voltage, but double the current. Is it also the same story? Double the I, same voltage, power is IV, so you still get more power. So that would have gotten rid of these two. And if you've learned anything at this point, hopefully you now quickly recognize if it's double, then it's half. So if it's double one, it's half of the other. So half of 30 is 15. That's my hand-waved approach. So anybody put A, how many did that hand-waved math, or how many did the math out and out? So hopefully that makes sense for that. And then it's math from that point on. Let me go ahead and do the math out and out for you. Power 2 divided by power 1 is going to equal B squared over R2, B squared over R1, because power is B squared over R. Those cancel because they're the same. So power 2 for power 1 equals 1 over R2, 1 over R1, which equals R1 over R2. So moving the math down here, I apologize, but power 2 equals R1 over R2, power 1, plugging in 30, 3 and 6. 3 over 6 is 1/2. 1/2 of 30, 15. So the math works. The math will get you there. But again, math takes too long. So how many are okay with the double the I, double the power, half the I? Because double the resistance, half the I, half the I, half the power. So I'm going to go on limb and say double I, double power. Yep. So what if their switch asked for R? Perfect story. So let's say they went around and said that you had half the power. So if they told you half the power here, then I knew it should be double the R. So cause and effect. If I double the power, it's because I have the R's. Could I say if I have the R's, I've doubled the power? Does that make sense that they could ask you whatever the inverted factor? So basically they're inverted. So if this is double power, it's half the R. If this is half the R, it's double the power. So, oh yeah, they did R1, same story. So let's say they say this is half the power, then it's double the R. If it's double the power, half the R. So either way, whatever they give me, you agree four variables. If 3 of them are known, you solve for the other one. If 3 of them are known, you solve for the other one. So either way. Yep. And that's the thing. But good question, because all of you should do this. I want everybody to do what she just did, and that is take a question as it's written and say, okay, how can they screw with me? What can they change? Well, they give me a different unknown. So they gave me, let's see, they gave me P1, they gave me R1 and R2 and solve for this. But if they give me this and this and made me solve for a ratio, that's one, or give me this and this, solve for that one. So many different ways to write the same question. The more you think about it that way, the better test taker you become. You're starting to think like a test writer, or maybe continuing. I don't know if you do this all the time, but it's perfect. It's what you should be doing. Last question. What is equivalent resistance for that grouping right there? 2, because side by side. Perfect. So is this a 2 in series with a 1? So I'm just gonna do my math real quick. C equivalent equals 1 times 2 over 1 plus 2. Does that help me at all? Perfect, 2/3. So best answer. You could have also said when you add two things in series, two capacitors, I should say, the equivalence goes down, so it's got to be lower than the smallest one. Only one choice was less than C. Also could have been A. Yeah. Just get everything in line, exactly. Take one local spot at a time, this parallel unit, turn it to this, and then it becomes an easier question. Okay, the last thing that I absolutely want you to click with, hopefully this seems okay. So hopefully your volume is high enough for this one. Oh no, shoot, I have it plugged in so you can't hear it. Failed again. It's a song that says electricity. Right, it's a disco song from years ago, but I have failed miserably. Oh, now I can't make the song stop. Oh, can you see, actually, can you see the speaker icon in the middle of it though? Okay, yeah. Oh, somebody needs to teach me how the heck to get that to feed into it so you guys get the punishing disco music as much as I do. But anyway, hopefully this makes sense and makes a circuit lecture down the road easier. This is one of those, practice is so key. And I mean, what was really cool is during the course of the lecture, how many noticed some of your peers hitting those moments of like, la la, I got it. It all fell into place. Homework will do that as well, hopefully. Yeah, I know. I need to get the sound options. On this one, it's all jacked up for whatever reason. So yeah, and I tried going to Zoom and Zoom offered no help. So I need to figure out how to do that computer-wise. But ooh, this is perfect timing. My iPad just ran out of power. Wow, that was fortuitous. So hopefully you can still hear me. My computer's still good to go, but my iPad just died. Perfect. Yeah, see you in office hours on Sunday. Yeah, so yeah, this is it. I'm sorry, now I'm just dragging on. So yeah, if you guys need to go, please go. But yeah, I'm hopeful that it was step-by-step and systematic. And admittedly, just in case, I know nobody records, but just in case somebody were to ever see this in a video format, they'd be able to get everything and move around. So I might be more cognizant of that than I should be, maybe, hypothetically speaking.